Welcome to today's Explainer. Picture this, you're a ninth grade science student in Pakistan, sitting at your neat study desk in a bright, sunlit classroom. The vibe is focused, you've got your notebook ready, and I am your friendly teacher here to guide you. Today we're going to demystify the fascinating world of radioactivity and atomic mass, step by step. If you've ever wondered how atoms actually transform, or how we figure out their exact mass, well, you're in the perfect place. Let's get started.
Here is what is on the whiteboard for today. 1. Decoding radioactivity and isotopes. 2. The mechanics of radioactive decay. 3. Real-world isotope applications. And 4. Calculating relative atomic mass.
Let's jump into Section 1, Decoding Radioactivity and Isotopes.
Okay, so to truly understand radioactivity, we have to zoom way in and look inside the nucleus of an atom. Sometimes, isotopes of the same element have nuclei that are just unstable. They are basically holding on to way too much energy. So, nature's way of dealing with that imbalance is radioactivity. The atom simply emits that excess energy out into the world as radiation. And when an isotope does this, we call it a radioactive isotope. Makes sense, right?
Now, here is something that might surprise you. Radioactivity isn't just limited to a handful of dangerous, obscure elements at the very bottom of the periodic table. It's actually a universal property. Literally, every single element known to us has at least one isotope that is radioactive. It's just a fundamental part of how matter operates in our universe.
Moving right along to Section 2, the mechanics of radioactive decay.
This is the part where chemistry feels a little bit like ancient alchemy. You see, when a radioactive element emits that radiation, it doesn't just lose energy. It actually undergoes a fundamental identity change. It transforms into an entirely new element. We call this process radioactive decay. And honestly, the craziest part? That brand new element might also be unstable, which means the decay process just keeps right on going.
Let's look at the actual math behind this magic. Take a look at how uranium-238 decays. It emits energy and boom, it transforms into thorium-234. But the chain reaction doesn't stop there. Thorium-234 is also unstable, so it further disintegrates into protactinium-231, releasing even more energy along the way. We see the exact same thing with bismuth-210 decaying into thallium-206. It's just this incredible, cascading chain reaction of elemental transformation.
To make this super concrete for you, let's think about the most basic element there is, hydrogen. Now, isotopes are just atoms of the same element that have slightly different physical properties. Tritium, which is a hydrogen isotope with 1 proton and 2 neutrons, is highly radioactive. But hydrogen's other 2 isotopes, completely stable, zero radiation. It's a perfect demonstration of how just a tiny difference inside the nucleus completely dictates whether an atom is stable or radioactive.
All right, Section 3, Real-World Isotope Applications.
So you might be thinking, okay, but why does this matter? Well, far from just being a hazard, radioactive isotopes are incredibly powerful tools. In medicine, doctors inject small amounts to diagnose complex diseases. Over in construction, engineers use them to test the strength of metals in concrete mixtures. They're the secret behind generating cheap nuclear power, and geologists even use them to map out and find hidden oil fields deep beneath the Earth's surface.
Let's compare two really specific examples to show you what I mean. In hospitals, doctors use an isotope called technetium-99. By pairing it with a specialized camera, they can literally track how fluids move through organs like your brain and lungs. But on the totally opposite end of the spectrum, archaeologists use carbon-14. See, when a plant or animal dies, it stops taking in carbon-14. So by measuring how much is left in an old piece of bone or wood, scientists can calculate exactly when that organism died. The older the sample, the less carbon-14 is left. It acts like a literal molecular clock.
And finally, Section 4, Calculating Relative Atomic Mass.
All right, time to roll up our sleeves. Here is our puzzle for today. We need to find the relative atomic mass of mercury, symbol Hg. Because mercury, just like a lot of other elements, exists as a natural mixture of different isotopes, we can't just pick one weight. We actually have to calculate a weighted average based on mercury's 7 different isotopes and their relative abundances. Basically, that just means what percentage of naturally occurring mercury is made up of each specific isotope.
Let's crack this math problem together step by step. And hey, don't let the numbers intimidate you. The formula is actually super straightforward. Step 1, we take the mass of each isotope, say 196, and multiply it by its relative abundance percentage, which here is 0.0146. We do that exact same thing for all 7 isotopes. Step 2, we add all of those newly multiplied values together into one big sum. And step 3, since we're dealing with percentages, we just divide that grand total by 100. See? Easy as that.
So, when you actually sit down and crunch those numbers, adding up all those products and dividing by 100, we arrive at our definitive answer. The relative atomic mass of mercury is exactly 199.387 atomic mass units, or AMU. It's a really beautiful example of how analyzing the precise natural makeup of isotopes gives us those standard values that we rely on every single day on the periodic table.
As we wrap up today's explainer, I want to leave you with a fascinating thought to ponder. We've seen today that every element has radioactive isotopes, and they are constantly shedding energy and transforming into completely new elements. So, based on everything we just learned, what invisible atomic transformations do you think are happening all around you right now? In the walls, in the air, or even in the objects sitting on your desk? Thanks so much for joining me in our virtual classroom today, and keep exploring the incredible science hiding just out of sight.